And the philosophy of aerospace engineering was, for decades, governed by the waterfall methodology. In this traditional paradigm, the development of a rocket engine is a linear, sequential process. Years of requirements gathering are followed by years of design, which are followed by years of fabrication, culminating in a series of tests where failure is viewed as a catastrophic setback. For organizations like NASA or legacy aerospace primes, a test stand explosion is a PR nightmare and a congressional inquiry in the making. At SpaceX, however, a plume of green flame and a shattered turbine housing are viewed through a different lens. They are the physical manifestation of a failed unit test. And to understand how the Raptor 3 reached its monolithic perfection, one must understand the agile hardware development cycle practiced at the McGregor, Texas, test facility. In software development, agile emphasizes incremental delivery, continual improvement, and rapid response to change. SpaceX has ported this entire culture into the realm of high-pressure metallurgy and cryogenic fluid dynamics. They have replaced the measure twice, cut once mantra of the 20th century with a new directive, test until failure, patch the kernel, repeat. In the McGregor test stand as a production environment in the world of DevOps. A production environment is where the code actually runs, and a staging environment is where it is tested under realistic conditions. McGregor is the ultimate staging environment. Here, the Raptor engine is subjected to stress testing that goes far beyond its nominal flight envelope. While traditional programs aim for a gold master design that remains static for decades, SpaceX treats every engine on the test stand as a beta release. And when an engine is bolted to the tripod at McGregor, the goal is not just to see if it works. The goal is to find the edge cases, the specific combinations of pressure, temperature, and vibration that cause the system to crash. In computer science, a developer might use a fuzzer to feed a program random data until it breaks, revealing a security vulnerability. SpaceX fuzzes the Raptor by pushing oxygen per burner temperatures to the metallurgical limit, or by inducing artificial pogo oscillations to see how the software-defined controllers react. And this is the continuous integration and continuous deployment of rocketry. In a standard CI/CD pipeline, every code change is automatically built, tested, and deployed. At the Star Factory in South Texas and the Foundry in Hawthorne, design changes are pushed to the hardware branch with startling frequency. A technician might identify a minor turbulence issue in a manifold. Within hours, the CAD model is updated, the commit, the 3D printers begin layering new superalloys, the build, and within a week, the modified engine is screaming on a test stand in Central Texas, the deployment. In the core dump of a rapid unscheduled disassembly, when a Raptor engine explodes during testing in event space, X famously refers to as a rapid unscheduled disassembly, RUD. The general public often sees it as a failure. To the SpaceX engineer, the explosion is a core dump. In computing, a core dump is a recorded state of the working memory of a computer program at a specific moment, usually when the program has crashed. It contains the vital diagnostics needed to understand exactly why the instruction pointer went astray. And a Raptor RUD is the most data-rich event an engineer can witness. As the engine tears itself apart, thousands of sensors measuring strain, heat flux, acoustic energy, and spectral emissions stream high-frequency data back to the servers. This is the stack trace of a hardware failure. By analyzing the millisecond by millisecond telemetry, engineers can trace the exception back to its source, perhaps a localized hot spot in the injector plate or a race condition in the startup sequence of the dual turbopumps. And because SpaceX builds its engines with a high degree of instrumentation overhead, they can see things that were invisible to the engineers of the Apollo era. They are not just guessing why a turbine blade failed. They have the high-speed video and the thermal mapping to see the crack propagate in real time. This allows them to debug the hardware with a level of precision that makes the traditional design-build-fly cycle look like ancient history. And embracing the hardware bug. In a traditional aerospace program, a design flaw is a defect that must be avoided at all costs through formal verification and endless simulations. The problem with simulations, however, is that they are only as good as the physics models they are based on. In the regime of full-flow staged combustion, the physics are so chaotic and the pressures so extreme that even the most powerful supercomputers struggle to predict the behavior of tripropellant gas mixtures, consisting of oxygen-rich gas, fuel-rich gas, and liquid methane. And SpaceX accepts that their simulations are lossy. They know that the production environment of a rocket plume contains Heisenberg's issues that only appear under specific, high-energy conditions that cannot be replicated in a virtual environment. Rather than spending 5 years and $5 billion trying to perfect the simulation, SpaceX spends 5 months building 10 prototypes and blowing them up. And this is a fundamental shift in the cost of failure equation. If a prototype costs $2 million to build, and its destruction saves $200 million in delayed development time, the explosion is a profitable event. By lowering the cost of each unit test through 3D printing and vertical integration, SpaceX has made it economically viable to learn through destruction. They have decoupled the risk of failure from the survival of the program. And the feedback loop, low-latency engineering. The true secret of the Raptor's rapid evolution from the messy, wired-up version 1 to the sleek, monolithic version 3 is the latency of the feedback loop. In most engineering organizations, the read or write cycle is incredibly slow. A test failure occurs, a committee is formed, a report is written, a design change is proposed, it is reviewed by a board, and a year later, a new part is manufactured. And at SpaceX, the write latency is minimized through a flat organizational structure and the proximity of design to manufacturing. The engineers who design the Raptor's turbopumps are often the same people standing in the control room at McGregor when those pumps fail. There is no handoff to a separate testing department. The developer is also the QA tester. And when a hardware bug is identified, the fix is implemented at the source code level, the CAD files, immediately. Because SpaceX owns its own foundry and 3D printing farm, they don't have to wait for a Tier 1 supplier to update their tooling. They simply recompile the engine. This allows for version 1.1, version 1.2, and version 2.0 to happen in the span of months rather than decades. The Raptor 3 is not just a better engine. It is the result of thousands of these micro-updates that occurred during the beta phase of Raptors 1 and 2. And stress testing the kernel, the pogo, and the surge. One of the most difficult subroutines to get right in a rocket engine is the start sequence. It is a delicate ballet of valve timings, spark ignitions, and pump spin-ups that must happen in a precise order within milliseconds. If the oxygen reaches the chamber before the methane, the engine runs lean and melts. If the methane arrives first, the engine runs rich and can experience hard starts, which are explosive pressure spikes. And during the iterative testing phase, SpaceX performed thousands of hot fire tests specifically to optimize this boot sequence. They deliberately injected faults into the sequence to see if the engine's onboard controller, known as the kernel, could recover. This is fault-tolerant engineering. They wanted to know if a valve lags by 10 milliseconds, can the software compensate, or does the system experience a kernel panic? And by chaos engineering their own hardware, deliberately breaking components to see how the rest of the system reacts, SpaceX built a level of resilience into the Raptor 3 that is unprecedented. The engine is not just reliable because it is simple. It is reliable because it has already survived every conceivable failure mode on the test stand. It has been hardened by fire. And from unit testing to integration testing, as the Raptor moved from standalone tests at McGregor to integrated static fires on the Starship launch pad at Boca Chica, the testing moved from unit testing to system integration testing. In CS, you can have a perfectly functioning function, but when you integrate it into a larger program, interface errors occur. And on the Starship booster, 33 Raptor engines must work in concert. This creates a distributed computing problem. The acoustic vibration of 33 engines is not just 33 times louder than one engine. It creates complex interference patterns and harmonic resonance that can shake the vehicle to pieces. The network latency between the flight computer and 33 separate engine controllers must be managed to ensure they all throttle and gimbal in perfect synchronization. And the early flights of Starship were, in essence, live integration tests. When engines failed to relight or were knocked out by debris, SpaceX didn't retreat to the drawing board for years. They treated the flight data as a telemetry log. They saw that the input and output, or the fuel lines, were being compromised by the external environment, and they refactored the engine bay. The evolution to Raptor 3, with its hardened kernel and lack of external soft tissue, was the direct patch for the vulnerabilities discovered during these full-scale system tests. And the philosophy of good enough to break there is a psychological barrier in engineering called analysis paralysis, the fear that if you haven't accounted for every variable, you shouldn't proceed. SpaceX breaks this paralysis by adopting a minimum viable product MVP approach to hardware. The first Raptors weren't perfect, they were good enough to break. And by getting a physical prototype onto the stand as quickly as possible, SpaceX gains ground truth. Ground truth is the ultimate validator. It doesn't care about your elegant equations or your beautiful CAD renderings. It only cares about the reality of high-pressure combustion. This bias for action allowed SpaceX to out-iterate the laws of physics. And the Raptor 3 is the stable release of this chaotic process. It represents the point where the bug reports have dwindled, the performance bottlenecks have been cleared, and the codebase has been cleaned of all unnecessary spaghetti. But this stability was only possible because SpaceX was willing to crash hundreds of times in the pursuit of a zero-error architecture. And the result, a deterministic machine. The ultimate goal of this iterative destruction is to move the engine from a stochastic probabilistic system to a deterministic system. In a stochastic system, you hope the engine works based on statistical models. In a deterministic system, you know it will work because you have eliminated every variable that could lead to an undefined state. And Raptor 3 is the first deterministic rocket engine. By integrating the sensors, valves, and plumbing into the monolithic structure, SpaceX has removed the external dependencies that cause non-deterministic failures. There are no more B-nuts to vibrate loose, no more wire harnesses to melt, and no more external lines to snap. The engine has been compiled into a single, high-performance executable. And this relentless pursuit of hardware truth through rapid failure has created an engine that is not just a piece of machinery, but a highly optimized algorithm for thrust. It is the physical embodiment of the SpaceX way, a testament to the idea that the fastest way to build something that works perfectly is to be brave enough to build things that fail spectacularly. And this culture of high-velocity iteration and live-fire debugging has transformed the Raptor from an experimental prototype into a mass-produced utility. This transition from development to operations is what enables the next great leap in aerospace. By treating the rocket engine as a reliable, hardened component rather than a fragile artifact, SpaceX has set the stage for a paradigm shift in how we access the stars. To truly realize the vision of a multiplanetary species, the rocket must move beyond the experimental phase and into the realm of routine infrastructure. And this shift toward a plug-and-play propulsion system is the final prerequisite for the most ambitious goal in the history of transportation: the transition from the sacrificial rocket to Section 9.1, the airline model, landing, refueling, and taking off again.